We spent 120 days designing a wind-powered vehicle, and you won't believe what happened by the end of it.
How do you move an 8.1 kilogram payload across a room with using only the power of a leaf blower?
For ME229, our challenge is to design a zero-emission, wind-powered cargo vehicle.
Here's the catch.
First, the system has to fit inside a 1 cubic meter bounding box. Second, safely transport heavy stackable weights across a 5 meter zone. Third, it has to accurately brake inside a 1.5 meter target area. Finally, we have to do all of this under 60 seconds and with the out-of-pocket budget capped at $25.
Before we built anything, we hit the literature. Highly cambered, large area profiles drastically outperform standard blades at low Reynolds numbers. We also referenced Atkinson's research on rigid sails, finding that an angle of attack between 10 and 30 degrees maximizes forward thrust. We realized quickly that capturing the wind energy efficiently was going to be the deciding factor.
For ideation, we used C-sketching and reverse engineering to come up with our 4 designs.
Our first idea was the wind wheel. Based off the water wheel, it uses its flaps to rotate and roll forward, and the masts are hanging in the middle.
But we scrapped it, because hanging a giant mast in the center of a rolling drum is not a great idea.
Idea number 2, the horizontal turbine car. This idea uses turbines to drive a chain, which then drives the rear axles.
But this is also a bad idea, because of all the energy loss due to friction.
The vertical turbine car uses a Savonius-style turbine to better catch the wind.
But we scrapped it, because it's hard to manufacture. Finally, we arrived at the sailboat.
Our funnel car is built of an MDF wood chassis. We kept the entire layout as low to the ground as possible so the wind hitting the sail wouldn't flip the car backwards off the starting line. We used bearings and a threaded steel rod for the axle. But for the braking system, we used string and spooled it around the rear axle. As the car rolls, the line unwinds. The second it hits the target zone, the line snaps tight, locks the axle, and throws the car into a controlled skid to a stop exactly where we want it. Now time for a construction montage. The entire point of our testing was to see how long our string needs to be in order to stop in the end zone. On competition day, we had 3 full runs just to get in the end zone, but it didn't go very well. Our first run ended a little short. Our second run went too far. Then the third run, the string decided to jam. It was a very unfortunate ending.